Hello everyone, welcome to another Quantum Mike Classic. I'm very busy right now with exams, so I wanted to bring back some Quantum Mike content that I created previously. If you didn't know, during COVID-19, I tried to do the Quantum Mike for the first time as a podcast. And in this podcast, I did interviews with people involved in physics, especially mostly physicists. Since I have a bunch of this audio recording, I thought it would be good to release it here on YouTube so you can listen to the interviews. They're quite good. Today, we're going to put on my interview with Mary Beth Laychak when I talk to her about the Canada-France-Hawaii telescope. So please take a listen and make sure to plug in your earbuds. Enjoy. Hello everyone, welcome back to the Quantum Mike. As always, I'm your host, Owen Darren. Today I'm talking to Mary Beth Laychak, who's the Director of Strategic Communications at the Canada-France-Hawaiian Telescope, which is on top of Mauna Kea in Hawaii. Today we'll be learning all about the CFHT from how it started to how it works. Thank you for joining me today, Mary Beth.
Thanks, Owen. Thanks for having me on.
Thanks for coming on the show. So this is a bit different since I talked to a few physicists, and today I'm talking to you about an actual larger project, which is more than one person. Now, I've always been very interested in these multinational scientific projects, and seeing that the CFHT is run by the National Research Council of Canada, the Centre National de Recherche Scientifique, and the University of Hawaii. How did this large cross-border project sort of come into being?
So we actually started in the early 1970s. And at the time, both Canada and France wanted to build large telescopes. The Canadians were thinking of building it in the very clear, sunny weather of Vancouver, Victoria area in that part of Canada, which, as we all know, is known for not clear and sunny weather. Not the best weather. And so, through a set of happenstances, the right people meeting the right people, Canada and France decided to join a telescope project together, and build one at the same time and invest together. And they were looking for a site. And in the early 1950s and 60s, Gerard Kuiper had actually done some site surveys on Haleakala, which is one of the largest mountain on Maui. He looked over and saw Mauna Kea and brought Alika Herring. And so Alika was a master lens maker. And so he was the one who actually made and ground all of the telescope lenses and mirrors for Kuiper's site survey experiments. And he was Hawaiian. And so they came over and they decided, after doing the site survey on Mauna Kea at 4,200 meters, that this was a great place for telescopes. And so they started to build telescopes around that time. And the University of Hawaii's Institute for Astronomy was a brand new program. It was actually started in 1968 or 1969. And they joined Canada and France in building the Canada-France-Hawaii telescope. And so we operate what's actually called the tripartite agreement. So Canada, France, and Hawaii, we are funded 42.5% by Canada, 42.5% by France, and 15% by the University of Hawaii. We have 3 resident astronomers from Canada, 3 resident astronomers from France, and 1 resident astronomer from the University of Hawaii. And so not only do they fund us equally, not only do they fund us in those, in that breakdown, but they also have access to the telescope in the similar amount. So Canada is 42.5% of our time, France the same amount, and the University of Hawaii 15.
Okay, so you said that they were doing a survey in Hawaii, and so what made Mauna Kea an optimal spot for telescopes?
So Mauna Kea is the ultimate spot for telescopes, in my opinion. And apologies to anybody who does all of the research in Chile, the deserts in Chile, and particularly we've seen what Alma's doing in the Atacama. But I would wager that the site on Mauna Kea is the best site in the world. It's definitely the best site in the Northern Hemisphere. There's a couple of factors. One, it's really high. So at 4,200 meters, we are at 40% atmosphere, which means that you have less atmosphere above. So light from space entering the Earth's atmosphere is distorted less. This works really well in the bands that excel on Mauna Kea, the infrared, the submillimeter. So while CFHT is not a submillimeter site, there are submillimeter sites on the atmosphere. There's less water vapor that gets in the way of their observations. And then the near ultraviolet, which is one of the areas that CFHT excels in. So we're at a high elevation. The weather patterns, the prevailing weather patterns in the tropics that we have give us trade winds. So we end up with a really steady airflow, really steady wind going over the summit. And when we think of mountains, we tend to think of the, jagged peaks of sort of the Andes or the Rockies or the Alps. Mauna Kea, Mauna Loa, all of the mountains in Hawaii were actually formed from a single hotspot in the ocean floor, creating a shield volcano. So this gives it, just imagine a shield flipped on its face, and you get a really even airflow across the mountain, meaning that we don't see as much turbulence in the air generated by the wind. Now, as I'm saying this, we have had some summer storms, and the weather at the summit for the past couple of days has not been great. So we do get bad weather. We do have a lot less sort of upper atmosphere royal. So if you think about, the U.S. mainland or the Canadian, Canada, right? When we look at the weather patterns in the summer, we get a lot of convection heating and thunderstorms. And that's because, you have land masses that are a different temperature than the air and the water. We're surrounded by thousands of kilometers of ocean on all sides. And so the ocean temperature is very, very stable. We don't get a lot of weather patterns coming out of that. Now, again, we can't have hurricanes. The weather isn't always perfect. We also have an inversion layer, which is a cloud layer where the cool, dry air of the upper atmosphere meets the warm, moist air of the lower atmosphere. And that forms a cloud layer that generally is somewhere around, I'm doing the conversions in my head, about maybe, so it's 6,000 to 9,000 feet. So that's 2,000 to 3,000 meters.
Something like that.
Roughly.
I've never been good at converting between imperial and metric.
So roughly 2,000 to 3,000 meters, we do have this cloud barrier, this cloud layer that forms. So if you were to come to Hawaii, you often see a band of clouds in between Mauna Kea and your field of view that almost look like it's going right across the middle. When the inversion layer is strong, that prevents a whole lot of tropical moisture from ascending on the summit. And so we end up with that drier air. Lastly, because it's a long list, Mauna Kea is actually one of the darkest places on Earth. It is even darker than some of the places we would see in northern Canada because we don't have any sort of auroral glow. Because we're so much closer to the tropics, there's no northern lights or any sky glow that we would see that brightens those northern areas. We also have fairly strict streetlight ordinances on the Big Island to prevent a lot of light pollution going upwards.
Okay, that's really cool. I'd known that the geography had an impact on the total. I never considered the mountain shape. That's really interesting.
Yeah, if you take like a side-by-side look of Mauna Kea or a Mauna Loa versus, Mount Kilimanjaro, or if you would think of it like, I don't know why Mount Kilimanjaro popped in my head, or Mount Fuji, or the Andes or the Alps or the Rockies. It's a really distinct mountain shape. Mauna Kea and Mauna Loa are massively, they're massive mountains. They don't go up to a sharp peak. It's sort of a round. In Waimea in my offices, I'm technically sitting on the side of Mauna Kea.
Wow, that's really cool. Now, you had said it wasn't the CFHT, or the telescope at the CFHT was it milliliter telescope or millimeter?
It's not, doesn't operate in the sub-millimeter.
Millimeter. It doesn't operate in the sub-millimeter. So actually, what sort of telescope is used at the CFHT?
So we are an optical telescope. Our mirror is 3.6 meters in diameter, and we're what's called an equatorial mount telescope. So if you can kind of imagine, you walk into our fifth floor dome, and you see a very large horseshoe shape that's brown, and then we have yolks coming back towards that, and then a part that goes straight up, and hopefully you can share pictures with your viewers because I can send you a photo.
I will, if you send me a link to the photo, I'll put it in the show notes for people to check out. And I will
Perfect.
definitely, people will see it on social media a little
I
bit before the
am
episode comes out.
I am not doing justice describing the shape of my telescope. And then you have the telescope part that goes upwards. And a mirror in the middle. So we have like I said, a 3.6 meter. We're optical near infrared, which means that we operate in light that your eyes can see, a little bit more purple and a little bit more red. And so we actually have 5 instruments, and we choose which instrument goes on the telescope based on the demand for that instrument, what programs do astronomers want to use, but also the phases of the moon, because our optical imagers is really impacted by the phase of the moon. If the moon background is too bright, then we can't use those 2 instruments.
Oh, I never thought about that. I never considered the phase of the moon would be impactful, but I can see that completely. Especially if you have a full moon, it'll wash out the night sky.
Right. And our specialty at CFHT, we have 2, is wide field imaging. So we have a wide field optical imager named Megacam. It's a 380 megapixel camera, so that images on the sky the area equivalent to 4 full moons. So if you can imagine, if you have 1 full moon and we're looking at this really large field of view, not only can you be washed out in part of the image where it's too bright, but you can also get a gradient of moon across it, and that's not good. We also have another wide field imager that's actually on the calendar now that's in the infrared. So its name's WIRCam, wide field infrared camera. And so we're using WIRCam on the sky tonight. The day that we're filming this, recording this, not yes. The day that you're listening. We also have another really interesting instrument that was developed entirely in Quebec, and so that's CITEL. CITEL is a Fourier transform imaging spectrograph that was developed in coordination with University Laval, ABB, and CFHT. So what that means is with CITEL, you get an image, that's the imaging part of the name. And then through Fourier transforms mathematics, they're able to take the information that they get on each pixel, 4 million pixels of this camera, and convert it into a spectra, which allows you to add a 3-dimensionality or a motion to the image that you have. So you can actually, what's really neat with CITEL is you can flip through the data cubes almost like it's a movie and see both, the image, but also how that image changes at different wavelengths. So allowing you to see, the composition or how gases, a specific gas, hydrogen or nitrogen, is actually moving within the object you're looking at. We have 2 spectrographs. Espérance. Espérance is an optical spectrograph, so it takes the light from one star and breaks it into its component rainbow. So from that, with Espérance, not only can you determine the composition, the temperature of an object, whether or not it has a planet, but Espérance is also a spectropolarimeter, which allows you to study the magnetic field of the star. And this is an area that's really exciting research and is done a fair amount in Canada. So the spectropolarimetry of hot stars is a topic that we have several PIs, primary investigators, astronomers who use our telescope, who do this kind of work living in Canada. And our last instrument is called Spirou. Spirou's an infrared spectrograph. So much like Espérance, it takes the light from a single star, breaks it into its component rainbow. You can also learn about the magnetic field. But what really sets Spirou apart is its precision in determining how a star is wiggling based on whether or not there's a planet around it. So it's essentially our planet hunter. That one's been on the telescope since 2018. And right now we're looking at existing planets the looking at existing planets with Spiru, trying to see what more information we can learn, as well as looking at planets that planetary candidates. So objects that have been identified by Kepler or TESS or some of these larger space missions that could potentially be a planet. We're doing the follow-up observations.
That's really cool. I honestly didn't know that the CFHT has such a wide range of sort of projects it can cover. And actually, talking about projects, so are when people use the telescope, are they only from groups such as the National Research Council here in Canada or the University of Hawaii, or can people from other organizations such as different universities book the telescope to be used? I know that certain other telescopes in like Chile, I've been made aware. I watched a YouTube channel done by an astrophysicist, and they were talking about booking telescopes. So how does that work with the CFHT?
So the way that it works is we're funded by those agencies, Canada, France, and the University of Hawaii. And with that funding means that we work for the Canadian, the French, and the state of Hawaii taxpayers, because that's where that money comes from. But that also means that any astronomer in Canada or any astronomer in France, regardless if they work for NRC, CNRS, or Waterloo, which is just a college that popped into my mind because we have PIs there. It doesn't matter what institution they work at. What they do in Canada and France is apply for observing time through something called a call for proposals. And the same thing applies at the University of Hawaii. So we'll put out a call for proposals, which is actually happening pretty soon here. We're talking in late July, and by mid-August, we'll probably be putting out our call for proposals. And that means that astronomers who want to use us go online and they fill out a form and upload their targets, and they give us an overview of the research that they want to do. Now, in the Canadian astronomers go to a Canadian time allocation committee. The UH astronomers, the UH and the French go to this time allocation committee. And these TACs, as we call them, they look through the programs and judge them based on the scientific merit. And then CFHT astronomers answer the question of, can we do this, yes or no? That's not, it's one might assume that the answer to that is always yes. Sometimes it's not. Sometimes we get questions and we get proposals that are kind of pushing our instruments to what we can and can't do. And other times we get proposals for objects that are not observable in Hawaii. They think we're farther south than we are, and those are rejected as well. Now, we then, as CFHT, are given programs. So we have Canadian programs, the ranked Canadian programs, the ranked French programs, and the ranked ones from the University of Hawaii. What sets CFHT apart from a lot of other facilities, although more are moving in this direction, is we operate in something called Q service observing mode, which means that you, Owen, if you were an astronomer and you applied for CFHT time, you would never come and visit us. We take all of the data for you. And so if you were interested, what's an area that you're interested in, Owen?
I'm actually doing an undergraduate degree in astrophysics. So let's see.
Yeah. What's your topic?
Okay, let's pick, I'm going to pick just pulsars. Let's just go with something basic, just pulsars.
All right.
I'm just going to pick, yeah.
So you decided that you wanted to observe a very specific pulsar and you want to use, and it's doing something special on a special day. Like, let's say that you want to observe this pulsar because it's been known to have flares of some kind where it has something different about it. So you want to look at this very specific pulsar. You will never visit us. You will complete a form for each of our instruments. And let's say you want to take the spectra of this pulsar. What you would end up doing is filling out your form, giving us the coordinates, giving us your observation constraints. What kind of image quality can you have? Can you take clouds? You can't. You're not going to be able to have any clouds, and you need the absolute best seeing we can get you. And so it's our job over the course of 6 months to take those observations for you.
Ah,
If you had been scheduled to observe at CFHT last night, the first half of the night we had some fog, so you would have actually lost out on that first half of the night. This way, it allows us to compensate for that and gives the opportunity for our trained remote observers. We've got 4 remote observers, that's their entire job. It also allows us to maximize the telescope time. So we might observe your pulsar one night, for 15 more, probably
yeah.
like 45 minutes. Then we might look at somebody who wants to see their star's transit for 5 hours. And then we might look at a couple of hot stars and kind of, bounce around with all of our different programs, each making sure that we're hitting the proper constraints for the
Hmm.
astronomer.
That's interesting. It does kind of take away the what I was thinking of. Oh, I'm going into astrophysics. I can go to Hawaii and write
You
it
can
off for work.
You can still visit. So we do sometimes, particularly for graduate students, our astronomers often will have, a graduate student or a postdoc who visits. We've done programs with, in conjunction with some Canadian institutions where they actually send out graduate students for a period of time. But yeah, the
Yeah.
long, kind of dreamlike nights of like, I'm going to go and be an astronomer and look through a telescope and sit in Hawaii. On the plus side, when you visit Hawaii for astronomy, unless you really take a buffer before and after, you are more or less just sleeping all day during our lovely weather. Right now it's raining, so
Uh,
I'm looking out my window. You sleep all day and you work all night, so you're not really enjoying Hawaii
yeah.
unless it's summer or
Yeah.
winter. Winter here is a lot nicer than winter in Canada.
Oh wow, I bet. Definitely probably not as cold. Yeah, all joking aside about being able to just visit Hawaii and write it off with a work thing, that does sound way more efficient to be able to do it. Then people don't have to reschedule their observation times.
Yeah, and there really is no rescheduling. So if you have a once in a lifetime or like a, once in a century event, or,
Mm.
maybe a little bit less rare than that, but you're looking for, your planetary transit and you come here and it snows or the weather's bad, you then have to reapply for telescope time. We're booked, all of our telescope time is booked down to the minute, down to the second over the course of an entire semester. We even have some, programs that we call snapshots that we can observe when the weather conditions aren't great. So there's really no time for rescheduling. And as much as your colleagues might like you, Owen, they're not going to be like, oh, well, Owen's pulsar is more important than my research, and give you their
Yeah,
observing time.
of
That
course.
doesn't, I'm not going to say it never happens, because I do know that sometimes you might have an astronomer who's visiting a place who says, I can do like 1 or 2 of your targets here if you do 1 or 2 of my targets there, and
Mm-hmm.
kind of some of those side deals. But as a facility, we're not able to do that. So it does make our way of the Q observing mode, it definitely has its pluses. I mean, there are some negatives. If you have, let's say, Owen, that you decide your first pulsar is way more interesting than you thought, if you were actually physically at the telescope, you could decide to take more observations of that one. At CFHT, you would look at your data and then come back to us and be like, I'd really like to actually change and observe this other target for a longer period of time at the expense of one of the other 3 that I gave you.
Mm-hmm. Ah, that's really interesting. It's a neat insight into how running the telescope sort of works. So, does the CFHT run its own projects as well, or research projects, or is it all the astronomers here just sort of get given projects from people who have booked time and they run that for them, or do they ever do something like? Is there anything run specifically by the telescope itself?
So our staff astronomers, excuse me, our staff astronomers have the option to do their own research, and they
Mm-hmm.
all do. And so they all do different research. And so they can apply for telescope time through their agency. So if they're a French astronomer, they can apply for through France. They can also ask for discretionary time. So that's time that's left to the discretion of our executive director. And so what he can do is look and see, okay, well, I've got this request for a target that is, unique, and they never would have known to put in for telescope time. So Oumuamua was a great example of that. We took some of the first observations of Oumuamua, that interstellar comet. That was done through discretionary time. It was a literal phone call to our director. Our staff astronomers can apply for that time as well. We also have at CFHT, in addition to these PI programs for individual astronomers, we have large programs. And so these are programs that are run, maybe you're not asking for 1 or 2 nights of telescope time, but you're asking for 50 nights or 100 nights or 200. And so instead of being run over the course of a semester, they're run for multiple years. Now, one of our astronomers here on staff, Laurie Rousseau-Neptune, who's one of our Canadian resident astronomers, she is the PI of Signals, which is a large program using CITEL. So she is running her own large program and also helping the astronomers who are using CITEL optimize their observations. And so that's really what our staff, our resident astronomers, do. Each one of them has an instrument that they spend most of the time working with, the one that they essentially specialize in. And as the instrument scientist, they help astronomers use that instrument efficiently, schedule our observations during our Q observations. They act as what we call Q coordinators, and then they do their own research. And so they might use CFHT, they might use other telescopes. They likely are using a combination of telescopes, trying to, do research in addition to working with other astronomers and working with the data reduction. That's a large part. So when you get CFHT time, you get data, we take it for you, the raw data, and then it goes through a data reduction pipeline to make that data more usable faster to astronomers. And so our resident astronomers also oversee those pipelines.
That sounds really efficient, like really, really efficient, which is pretty cool.
Yeah, all of our data is available publicly at the Canadian Astronomical Data Center, the CADC. And so our astronomers, so you, Owen, with your pulsar time, that is your time, proprietary time for a year and a half. If you're a graduate student, it's a little bit longer. Once that time's up, it's publicly available at the Canadian Astronomical Data Center's website. And you can go and download it. And there's been we've been in the news a little bit lately. Our archived data was used in the rediscovery of a couple of lost moons of Jupiter. And Sky and Telescope had put together an article about the discovery of an additional moon of Jupiter. It turns out it was one that was already known, but that was done by a student named Kai, actually, who had taken our archival data and ran it through some software and made these discoveries. So anyone listening can go and download this data and take a look at it.
I didn't actually know that there was archived data. I've been looking to just sort of find some data from other projects and just sort of look at it myself, just to get an idea and maybe play with it. So that's new to me and really, really fascinating. Now, I've heard that the CFHT has an upgrade coming up called the Mauna Kea Spectroscopic Explorer, or the MSE. Would you mind talking about that?
Sure. So MSE is our plan to reimagine CFHT. So we are a 40-year-old facility. And one of the things that CFHT has always done really well when you look at the 3-meter class of telescopes in the United States and around the world is that the scientific productivity of these size telescopes, the 4-meter class, as we call them, not everybody's at the same level as CFHT. And that's because we've looked at the publication level. We've looked ahead and we've been planning and seeing what's next down the road. And so MSE is our next attempt to do that. So this is a project that we have to, like I said, reimagine CFHT. So essentially we want to take our 40-year-old building. Our telescope facility on the summit is 5 floors. So we want to take the first 4 floors and essentially not really change them. We might we're going to remodel some rooms. But the concrete pier that holds our current 42-year-old 4-meter telescope can actually hold the same can actually hold the weight of a 10-meter class telescope. Telescopes designs have changed over the past 40 years. They use a lot less steel than they did 40 years ago. And so this has allowed the size and the mass to actually be very, very comparable. So what we plan to do is put a new telescope, 10-meter class, on that same CFHT existing pier. And with MSE, the telescope will be fully dedicated to spectroscopy. So that idea of we're taking light from a single star and breaking it into its component rainbows. At CFHT now, both of our spectrographs can look at, one target. Espérance and Spirou can look at one target a night. MSE aims to look at about 3,000 to 4,000 targets per night, not per night, per image. So they will have 3,000 fibers, and each one of these little fibers can be put on a different object or on the sky to get background measurements. And that's where we get multi-object spectroscopy. And so the idea is that we're seeing in astronomy now, and over the past decade and moving into the 2030s, projects like the Vera Rubin telescope. I was going to call it by its old name, LSST, but the Vera Rubin telescope, that's an all-sky telescope. We're seeing projects in space like Gaia and Euclid that are generating lots and lots and lots of images. And so with these large surveys, who's doing the spectroscopic follow-up of the objects that are discovered and unveiled? And so that's the plan for MSE. We are in our design phase and currently looking for additional funding to, continue moving forward with the project. So if you know anyone, Owen, who wants to fund a telescope in Hawaii, you can let me know.
If I meet anyone, I will let them know. That's really cool. The only other project that I'm currently aware of that's being upgraded is the LHC. I'm at Carleton, which has a lot of people who work at CERN. So that's the only comparison that I can think of. But this is kind of different. You're completely changing your telescope. When the people at CERN, they're just upgrading some panels so they're a bit more sensitive. This is almost like a bigger upgrade, which is really cool.
We're going to swap out the telescope, swap out the instruments, get a brand new dome. It'll be about 10% larger than our current dome. So what's really cool for me is when I see I have a great image of CFHT on the mountain and an image, a rendering of MSE. And when you look at them side by side, the size doesn't look different at all. It's a different kind of dome. We're going from a dome that opens, traditionally like what you think of when a dome opens to what's called a Kalat dome. So how the dome opens and closes looks a little different. Is a little different. But when you look at them side by side, the size is so similar. Like I said, 10%. It's hard to notice a 10% difference unless it's immediately side by side.
That's really cool. I actually follow the CFHT on social media. I have been for a little bit. It's really fun to keep track of. So I'm actually looking forward to that a whole lot, especially hearing more about that. And actually talking about social media and the CFHT, is there any outreach done by the telescope? I assume that you would know about this since you're the director of strategic communications at the telescope.
I am, and that is actually my job. And so I've lived in Hawaii for 18 years now. I started off working as a service observer. So I used to work at the telescope taking observations for astronomers. I've spent about 500 or 600 nights on the summit taking observations. So I actually have a bachelor's degree in astronomy and astrophysics. And then when I moved to Hawaii, I realized, and I started in college a little bit, but I realized that, what my passion really was is explaining astronomy to people. And I did not know that was a career you could have until I moved to Hawaii. And so after learning more about, the work that's done in outreach and community engagement here, I decided to get a master's degree. So I have a master's degree in education with a concentration in educational technology. And so that kind of work really puts me in a unique position to do the job that I have. And so fundamentally, my job is explaining astronomy to people. So we have a lot of outreach events that we do here at CFHT, not only us as a single facility, but the Mauna Kea Observatories as a collective. We do and sponsor outreach activities together, very common. I was actually in, you mentioned it today. So today, if we kind of look at my day's a good sort of example of the kinds of different projects we do. School is starting here in Hawaii, and today is the first day of school for teachers at one of the elementary schools that I work with. So I've worked with the school for about 7 years. I'm on their school and community council. And so the principal, every first day of school for teachers every year, he makes breakfast. So I go and I help, and I made waffles. And so while making waffles, I was chatting with all of the teachers that I've seen, haven't seen during COVID. And so we had a good conversation about, what are they interested in for their students? So fourth grade wants to learn more about phases of the moon. And the teacher was really excited to learn that we have some new videos that I thought she would really enjoy. And then another meeting, then another teacher wanted to talk about how we can she'd like to bring some of the new, like when she sees it in the news, content into the classroom. So while on the surface I'm making waffles successfully, thank you, making waffles, I'm having, a conversation and reconnecting with these teachers, reminding them that, myself and CFHT, we're here for them in their educational needs and, supporting the community. I went from that to a call with MSE because I also actually work for part of my job is, a lot of my job is working with the MSE team and working to kind of, pave the way for MSE here in Hawaii. And the idea amongst, people who live here that, MSE they see it as an upgrade and something that's really good for the community. But also strategically thinking down the line, how can we do outreach in a really new and engaging way where we're maybe moving outside kind of the bounds of the traditional classroom visits and doing some new kind of fun and exciting things. And then I went to a planning meeting about the James Webb Space Telescope. So JWST, we have no part in it at CFHT, other than we have some dear, dear friends that are deeply, deeply involved working on the project. But we want to hold a community event, COVID permitting. And we also were having a discussion about how to incorporate larger aspects of science in Hawaii through a self-guided tour of all of the different kinds of science that we can do. The past year with the pandemic has been really challenging in outreach. We've made a lot of videos, so you can find our videos on our Vimeo page. We also post them on social. We also work across the Mauna Kea Observatories and have this whole collection of videos on YouTube on the Mauna Kea Observatories channel, which is known as MCALC. We call it MKO at Home. And so we had to rethink one of our signature events, the solar system walk. So we made it self-guided. There are QR codes, decals that you can print out. And so this walk can be done literally anywhere. So if you would want to do one, Owen, in your town, or anybody listening wants to do one, we have all of the materials that can be printed, they can be posted, and then there's a QR code that links to videos describing each of the planets. And so that's the kind of work that I do. I also run a program called Mauna Kea Scholars, where Hawaii public high school students can apply for telescope time on the Mauna Kea observatories for their own research. So I work with high school students to come up with an idea, develop it, submit research proposals, and then ultimately receive telescope time, not only at CFHT, but at all of the telescopes on Mauna Kea. Yeah, and I manage our social media. And so we have there's a lot of outreach events that we do. I'm happy that we're going to be, right now it's very weird in Hawaii with COVID. We're on a bit of an uptick because of the Delta variant. So that's probably going to put some changes into what we're doing in the next couple of months, what I'm doing in the next couple of months. But, over the past year, we've really hit videos hard, done a lot of virtual talks. I think I've talked to a good eighth of the astronomy clubs in Canada, the RASC clubs in Canada. I was doing some math. I've done a fair number. There was a while where I had one or two like every week. And really happy to be able to do that. That was something that I couldn't do before. So for
Ah.
Canadians, so you as a Canadian student and all of the Canadians listening, we do have projects that we work on in Canada. I work a lot with a program called Discover the Universe that's run by a woman named Julie Bulldog-Duval. And Julie has absolutely wonderful resources for teachers. And so we actually partnered with her and the Dunlap Institute on a project over the summer to have videos about the annular eclipse that occurred in northern Canada.
Mhm.
One of our resident astronomers, Lori, is First Nations. And so she took two First Nation stories and adapted them. And we recorded a video of her here in Hawaii. And then working with Julie and Dunlap, those videos were translated into 6 First Nations languages. And then Julie and her team put all of the videos and other information that Discover the Universe and Dunlap created on flash drives and mailed them to teachers across northern Canada and northern Ontario to see if there was any teachers that were interested in receiving these materials so that they could better understand the eclipse with their students.
That's awesome. That's really, really, really cool. And I know it's a lot of reallys to say, but it truly is. I was about to say it really is, but that's one too many reallys. Actually, you had mentioned the QR codes, for example, one of the projects, and I'm sure with the other stuff with outreach, where should people be contacting the CFHT to either get the stuff for the astronomy walk, or just for any sort of interest in the telescope?
So I can actually give you some links for that. We have a page on our website that is has the information about what we call the Waimea Solar System Walk that can be adapted. We are follow us on social media. I can give you, we're at CFH Telescope on Instagram, Facebook, and Twitter. We also have a Vimeo page, and so Owen, I can give you the links for all of those that you can put in the show notes. So if people want to watch the videos, all of Lori's videos are actually on our Vimeo page. And you can also look up Discover the Universe. I think if you just Google Discover the Universe, you'll be able to find Julie's website.
That would be awesome. Yeah. For those listening, if you're interested in anything CFHT related, there will be lots of information in the show notes and the description. Now, actually, talking about social media, especially, I've noticed, and this is something that I think is very specific to the CFHT. I've never seen it anywhere else. You have the little solar system plushies, and you constantly are
Yes.
doing stuff with them. Venus, I remember weeks where Venus is traveling to different telescopes. Where did that idea kind of come from? It seems so out there, but it's so cool.
So Owen can see it because he can see me while we're recording this. But in my office, I have all of the CFHT stuffed planets, and so it sort of started a combination of ways. I'm really careful, and I have the philosophy of being really careful to not show kids on social media without their parents' explicit permission.
Yeah.
So if I'm visiting a school, I want to show that I'm visiting the school. We want to talk about the school visit on social, but I don't want to put a kid's face on social media unless I've, talked to their parents. So oftentimes we can use the stuffed planets as a proxy. So it might be a picture of the stuffed planet visiting the classroom, or what I often do, depending on my activity, is there's a lot of hands and UV light bracelets because I make a lot of those. I also get tired of talking about on social media where I go and the things that I do. And like Mary Beth went to Waikoloa Elementary School. Mary Beth went to Honokaa Elementary School. So if the stuffed planets can have their own persona, they're the ones having these adventures. They're the ones traveling. They're the ones doing all of these things. I don't have to post about myself as much, which is good because that's always, as the person who plans the social media,
Mm-hmm.
with my coworker who ultimately posts, being like, well, I'm going to do this. Let's post about me. I'm actually fairly disappointed because in the lead up to COVID, last summer, I knew I had some big plans of travel. I was going to go to a couple of places. So I bought a Baby Yoda because Baby Yoda was going to travel to all of these places. And Baby Yoda is in my dining room. Hasn't moved to my office yet. I also use the little stuffed planets. They're from a brand called Celestial Buddies. I use them when I talk to students to make it more engaging and more physical for them. So instead of, a student, when we're talking about the phases of the moon, one holds the moon, one holds the earth, one holds the sun. They stand up in front of the class. They physically move how the earth and the sun would move. Sometimes I get a really bright mag light and I actually shine it over the student who's the head, who's the sun, over their head, so that they can see how the moon looks differently as the other student moves around. So it gives an opportunity for a little bit more physical motion and physical engagement. Also, if we're talking about the solar system, I want to do a combination of planet and scale. I might make depending on the age of the students, we might do a full mini solar system walk where we take 5 or 6 steps, or 37
Mhm.
steps, or 75 steps, depending on, which planet we're going to. And the kid physically, that each kid's a planet, and they physically set it down. So the stuffed planets, they're big, they're fan favorites. We get questions about them. And we're actually going to be unveiling in August
Ooh.
some new, where is the comet, the CFHT comet. Now, sadly, because of customs, we do often limit our prizes to just the US, because sometimes the
Hmm.
difficulties of going to mail something through customs for our lovely administrative assistants can be a little bit tricky, but
Yeah.
we'll see. Maybe we'll do a contest soon, where we'll open it up to Canadians.
Well, for those listening, especially in the US, follow the Canada France Wine Telescope in case there is a contest. Well, we're kind of wrapping up to the end of our time. So before we finish up, I thought I would ask sort of a bit more of a personal question. What do you think is the most impactful experience that you have personally had working at the CFHT?
Hmm. So I probably I have a couple. I have a science one and a not science one. So when I was observing, one of the things that I was personally responsible for observing was something called the Deep Impact, and that was in 2004 when NASA crashed a probe into a comet. And so
Mm-hmm.
telescopes all around the world were watching um, this comet, and we knew the moment of impact. And most people were taking spectra. They were doing spectroscopy to see what was the composition of the comet, what was it outgassing. We were taking images, and so I was actually able to sit there and watch over a series of, like, we were taking images like every 20 seconds, over time, watching this comet get brighter and brighter and brighter and brighter and brighter, and then reach a maximum, and then fainter and fainter and fainter and fainter. So that was a really cool thing to do, and a really cool observation, because I knew that I was one of the only people actually looking at that. We had the astronomers who were getting the data in almost real time. They were doing their thing, but I was like just looking at it, making sure that it was where it needed to be, and that the observations were good, and that the camera was happy. And so that was just one of the coolest things I had the opportunity to kind of see and work with. And then, in the work that I do with CFHT, in my director of strategic communications job, just knowing that I'm working with students, and when those students kind of come back, or when I see them as an intern. So actually two of my interns now are students that I worked with through Mauna Kea Scholars when they were in high school. One's majoring in astronomy, one's majoring in elementary education. And so for me, I'm exceptionally proud of both of them when I hear that they're doing well or succeeding. Or when I see like a kindergartner at the grocery store who says, "Hi, Auntie," or they come back to an event and say, "This is the event that I come to every year," and they're like 8. I've been coming here since I was a kid. And the person telling me this is 10, right? I've had that happen multiple times. So like those are a lot of tiny little experiences that really add up to feeling as though, um, I'm helping kids open doors for themselves and see themselves maybe as a scientist or somebody that can do science or somebody that can do engineering or STEM or, be a machinist and work at the observatory. What we think of as STEM can be really narrow, but it's a much broader category. And I really want kids to feel as though that's an opportunity that exists for them, from like kindergarten onward. And, maybe you don't become an engineer or a machinist, but if you have that idea that you have that potential within you, you're going to go and do all of the other wonderful things that you want to do, like be like the most amazing elementary school teacher ever.
Of course. Well, hopefully this interview with you, which has been very enlightening, very detailed oriented, and I thought it was amazing, has hopefully taught some people about the wide range of stuff that's going on at the CFHT and just what they can potentially do with their degree. After all, you started with an astronomy degree and now you're doing this job.
Yeah.
So with that, we're just going to wrap up. Thank you very much for having this Zoom call with me and agreeing to do this interview.
All right. Well, thank you for
amazing. Thank you for listening to this episode of The Quantum Mic. Join us next time for another episode of Relative Greats, where we will be talking about James Clerk Maxwell, the man who took the first colored photograph and one of the greatest physicists of all times. You can follow The Quantum Mic on Twitter at quantum_mic to stay up to date with the show. Let us know how we did by leaving a review and subscribing to our show. This episode of The Quantum Mic was hosted and produced by Owen Dara. Episodes were edited by Owen Dara. The Quantum Mic was created by Owen Dara. And the music used in this episode is by Kevin MacLeod. Thank you for listening, and we will hear you next time on The Quantum Mic.